Well, hello. I'd like to welcome you to the wonderful realm of calculus that we call related rates. And there's a reason why we call this section related rates. Basically, what we've got is we've got some real world application problems. And oftentimes, in real world math problems, we have multiple variables, okay, that are changing at the same time. And we would like to establish a connection to them or relate them between different rates of change, and those are derivatives, okay? So we have different rates and they're related. So that's why we call it related rates. So what I want to do first is go through this example here. And the example here is really the algebra involved in related rates. And one of the things that we do talk about with related rates is that we always use implicit differentiation in the chain rule to figure these problems out. And the main thing that I want you to write here is that we take derivatives with respect to time. With respect to time t, okay? So what I want to do is take a look at this equation here. And the algebra example that we have is we already have the equation we're given, and we want to find the derivative of y with respect to t when x is equal to 4, and if we know that dx dt is equal to 2 when x is equal to 4, okay? So what I'm going to do here real quick is I'm going to zoom in here, and I'm going to take the derivative with respect to t of this entire equation. So ddt of y is equal to the derivative with respect to t of 5x squared, okay, minus the derivative with respect to t of 6x, and then plus the derivative with respect to t of 2, okay? So, as a result, we have to look at this and we have to say, all right, the t and the y don't match, so I have to use implicit differentiation, okay? I have to take my normal derivative and then multiply by dy dt, okay? So let's go ahead and do that. The normal derivative here would just be 1, so I'm just going to get dy dt here, okay? dy dt. And this is equal to, if I took my normal derivative, then I would just get 10x, but then I have to multiply by the derivative with respect to x of t, okay? Because, guys, these don't match. The t and the x don't match. So I need to multiply this by dx dt. And let me erase that so it looks nice. Okay, so dx dt. Okay, and then minus, okay, the derivative of 6x would just be 6, but then we have to multiply that by dx dt. Okay, and the derivative of a constant 2 would just be 0. Okay, so now here's what we know. Okay, we know that x is equal to 4. Okay, and we know that dx dt is equal to 2, all right? So let's go ahead and plug those values in. And so I get dy dt is equal to 10 times x, which is 4, okay? So 10 times 4 times dx dt, which is 2, okay? And then minus 6 times dx dt, which is 2. All right, so if I evaluate this, dy dt, I'm going to end up getting 10 times 4 is 40, times 2 again is 80. Okay, minus 6 times 2, so minus 12. And so we end up getting that dy dt is equal to 68. Okay, and when I write that, all right, this just means that the derivative with respect to y, the derivative of y with respect to t is 68, okay? And again, guys, this is the algebra involved here. And so this one's pretty simple because we're not given a real-world situation here. We're just given the algebra. But you need to know that and understand that dy dt is just a rate, and that dx dt is a rate, okay? And so what I'm going to do is I'm going to go ahead and stop this video, and I'm going to continue on with another one here in a second, but we're going to use this strategy here to solve this problem, okay? So, or to solve the next few problems. So I hope you enjoyed this video. Hopefully it was, you know, just the algebra portion of it, so it's not too terrible. But let's go ahead and I'm going to stop this, and we'll go ahead and do the next video.